In this section, we'll look at rational functions. Rational functions are functions that are in the form of fractions, and we'll look at how to graph them. So first of all, we're going to talk about domain. Remember we talked about at the beginning of the chapter, or actually last chapter, that domain, when you have fractions, has to do with the denominator. Remember, you set the denominator equal to 0, so here we'll have x minus 5 equals 0. We'll add 5 to both sides to find x. So we find out that x equals 5. And remember that that really means that we have 5 on a number line that we're crossing out because we can't have 0 in the denominator. So our domain is everything to the left and everything to the right. So we have negative infinity to 5, union 5 to infinity. Let's look at the next one. The next one we have x squared minus 25 equals 0. You can solve this in a couple ways. We could factor it, or we could just add 25 to both sides. And then we'd have to take the square root of both sides. But remember, when we do that, we have to take a positive and negative because every x squared equation should have two answers. So that gives us x is equal to positive 5 and x is equal to negative 5. And again, remember that really means that on our number line, we have those two numbers and we want to cross them out. We can't use those numbers because that gives us 0 in the denominator. So we want everything to the left, everything between, and everything to the right. So we'd have negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. Okay, let's look at one more here. Here we have x squared plus 25 equals 0. We can do the same thing here. We'd subtract 25 from both sides. It gives us x squared equals negative 25. And when you take the square root of this, we end up with x is equal to a positive 5i and x is equal to a negative 5i. Remember that I comes from the negative inside the square root. So here's the thing with domain. Domain only talks about real numbers, and these are not real numbers. So they don't show up on a number line. So we can't cross them out on a number line, which means that our domain is just negative infinity to positive infinity. There's no real numbers that are going to mess this problem up. So in this problem we're going to talk about, and the next thing we'll talk about is arrow notation. And arrow notation is just a way of looking for y values at certain x values. So we'll just look at that in the next example. So in this example, part A says that x is going to negative 3, and that little negative sign after the 3 means from the left. So we're headed towards negative 3 on the x number line, but we're coming from the left. And we're trying to ask ourselves, what's the y, what's the graph doing as we trace it in that direction? Well, the y value is headed straight down, so that would be negative infinity. So let's look at this now. This next one says we're approaching negative 3 from the right. So that means I'm going to negative 3 from the right. That means I want to trace my graph along that spot. And you can see it goes up. So the y value is going towards infinity. So this one says we're going to approach 1. X is going to 1 from the left. So x is going to 1 from the left. Here's 1. So that means we want to trace it this way. And you can see it's going down. So that's negative infinity. This one says we're going to 1 from the right. So here's 1 again, but we're coming at it from the right. So we're going to trace the graph in that direction. You can see it's going up, so it would be a positive infinity. So the next one is saying x is headed towards negative infinity. So that would be x going out this direction. So as I follow the graph out that direction, it's getting closer and closer to the x-axis, which is where y is equal to 0. And you can see each time it says f of x is going towards f of x. Remember, f of x is the same thing as y. That reminds you, or should remind you, that we're really looking for y here. Okay, so let's do one more here. This says x is going to infinity. So that means that we're following the x-axis out this way. So I want to trace the graph out that way. And that's getting closer and closer to the x-axis, or the y value of 0. Vertical asymptotes are like magnetic walls in the graph. They happen where the denominator, let me try that again, equals 0. The graph cannot touch or cross a vertical asymptote. We draw these with dashed lines. So it's essentially another way of crossing out those spots where the bottom of that fraction is equaling 0. So here it says find the vertical asymptotes. So we'll start with this first one. Here we have x squared minus 1. We'll set it equal to 0. In this case, we can factor this. We'll have x plus 1, x minus 1. It's a difference of squares. X is the beginning of both, 1 at the end of the both, 1 plus, 1 minus. We'll set each one equal to 0. And we'll solve. And here we have two vertical asymptotes. So let's look at the next one. We'll talk about how these asymptotes look in a minute, but right now we're just trying to find them. So let's look at this next one. The next one says that we have x squared minus 1 equal to 0 also. So what's the difference between these two? Well, let's look at the original function here. In the original function, I'm going to do it down at the bottom, we have x minus 1 over x squared minus 1. And if I factor that bottom like we did here, this x minus 1 cancels out. So that means that this can be simplified to 1 over x plus 1. So rather than starting with this as our function, we really want to start with g of x is equal to 1 over x plus 1 for the vertical asymptotes. If we can cross it out, then it doesn't give us a vertical asymptote. So now we're ready to start with a denominator here. We'll do x plus 1 equals 0. I'll subtract 1 from both sides and get x is equal to negative 1. And that's the only vertical asymptote in that problem. Alright, so let's look at the next one. So now I have x squared plus 1 equals 0. X squared plus 1 does not factor. We can't factor something that has a plus between them that squares, only if it has a minus between them, like in part B. So this doesn't factor, we just have to solve it the way it is. So I'll subtract 1 from both sides. And then I would take a square root. But this would give me I and negative I. Remember, because of this negative underneath that square root. So the problem is that I and negative I are not real numbers, and therefore they aren't vertical asymptotes. So part C does not have a vertical asymptote. Horizontal asymptotes are like magnets, but they tell what happens on the outside edges, and they are based on the degree. So if the degree of the numerator, the top, is smaller than the degree on the bottom, then the horizontal asymptote is y equals 0. So again, that happens when the degree in the top is smaller than the degree on the bottom. If the degrees are the same, then you have a fraction for your horizontal asymptote, and that's found by using the leading coefficients. If the degree on the top is larger than the degree on the bottom, then it does not have a horizontal asymptote. So let's look at this. The degree on the top is 2, and the degree on the bottom is 2. So those degrees are the same. So we'll have a horizontal asymptote at y equals, and then we use the leading coefficients. That's the numbers that are in front of those x squareds. So we'd have 9 over 3, and that reduces to just y equals 3 for our horizontal asymptote. Here, our degree on the top is 1, and the degree on the bottom is 2. Because the degree on the top is smaller than the degree on the bottom, the horizontal asymptote is automatically y equals 0. And here, the degree on the top is 3, the degree on the bottom is 2. Because the degree on the top is bigger than the degree on the bottom, there is no horizontal asymptote. Okay? Notice when we did vertical asymptotes, they were x equals, and that's because every vertical line is x equals that line. We talked about that in chapter 2. These horizontal asymptotes are always y equals. That's because every horizontal line is a y equals line. Again, that was in chapter 2. So finally, there's these 7 steps for graphing a rational function. The first thing is symmetry, and we'll talk about that in a minute. We haven't done that before. But then we can find the y-intercept, and we've done this in several different situations. But you find the y-intercept by making x equals 0, and then the x-intercept by making y equals 0. And that's the same every single time. Then we'll find the vertical asymptote by setting the denominator equal to 0. And then we find the horizontal asymptote by looking at the degrees. And then finally, we have to plot points. And then we connect the points with the curve, not crossing asymptotes. Okay, so let's try a few of these. Okay, so first let's look at step 1. And step 1 is symmetry. So in this case, we're trying to see, do we have even or odd symmetry, and that can help us graph things. So first we'll look for even. And to find even, we replace x with negative x and simplify. So I'd have 3 times negative x minus 3 over negative x minus 2. And this would give me negative 3x minus 3, negative x minus 2. This is not the same as the original, and by the original I mean this one up here. So it's not even. So then to look for odd, we take a negative 1 times the original function. Okay, and usually that means we just -1 times the top. This is in parentheses. So for even, we replace x with -x. Maybe I should write it up here. Replace x with -x and compare to the original. For odd, we multiply by -1, and then we compare to f of -x, which is what we found when we were trying to do the even. So what I mean by that is here, where we have -1 times the top, we would get -3x plus 3 over x minus 2. So I take this and I compare it to this. Okay, for even, we compare back to the beginning, but for odd, we compare back to the even part. And if these are the same, then it's odd. If they're not, then it's not. So these are not the same, so not odd. So that's step 1. So let me get some more room so we can move on to step 2. So step 2 is the y-intercept. And remember, that means that we make x equal to 0. So we have y equals 3 times 0 minus 3 over 0 minus 2. 3 times 0 minus 3 is just -3, and 0 minus 2 is just -2. Those two negatives cancel out and leaves me with 3 over 2. So I find out now that my y-intercept, remember x is 0, is 0, 3/2. And I can put that on my y-axis right there. So step 3 is x-intercepts. Remember, that means that we make y equal 0. So we have 0 is equal to 3x minus 3 over x minus 2. So to solve this, I have to multiply both sides by that denominator because I want to get rid of the denominator. And on the right side, it cancels out, leaving me with just 3x minus 3. On the left side, 0 times x minus 2 is just 0. So then I'll add 3 to both sides. And I get 3 is equal to 3x I'm going to write that over here just because I'm sort of out of room right there. So then I divide both sides by 3 because that's what's in front of the x, and I get 1 is equal to x. So that tells me that the graph is going to cross the x-axis at 1. Okay, so let me create a little bit more room for our next couple steps. Step 4 is about our vertical asymptote. Okay, and the way we find that is we take the denominator and we set it equal to 0. Again, this is like that domain. We're really figuring out what's going to mess up this problem. So that gives us x is equal to 2. So the way we graph that is that we need to cross 2 out. The way we cross 2 out is that we put a dotted line, it's a vertical line, across 2 on the x-axis. It's crossing out that number x value of 2. We can't have 2 as an x value. So step 5 is our horizontal asymptote. Remember, that happens by the degree. The degree on the top is 1. The degree on the bottom is 1. So we use the numbers in front of those x's. It would be 3 over, and this one really has a 1 in front of it, over 1, which is just y equals 3. So that's a horizontal line on the across the y-axis. We put a dash in that's on 3. So we've done a lot of the work now. We have smooth curves, and this vertical asymptote tells us that there's a curve on this side of the asymptote and a curve on this side of the asymptote. Well, on this side over here, we've already got points. We know that we have these 2 points. We'd need to connect them, and then it would need to go towards this vertical asymptote, and as it goes out, it would come towards the horizontal asymptote. So that left side's done, but now we need something on this right side. And the way we do that is by plotting points. We need a point, at least one point on this side of that x, this vertical asymptote. So you can choose anything we want. So let's say I choose x equals 4. You can choose other x's if you want. I'm going to stick that back up into this original problem. So I'd have y is equal to 3 times 4 minus 3 over 4 minus 2. So it would be 12 minus 3 is 9 over 2, and that gives me 4.5. This is a point. X was 4, y is 4.5. So I'd plot that, and I get a point right there. And that's enough to tell me that this other piece on this right side is above that horizontal asymptote. So as it comes out, it would come towards the horizontal asymptote, and as it comes left, it would go up along the vertical asymptote. And that's my graph. We'll do the next couple examples in a separate video.